Okay, it is starting. Great. Okay, so let's jump into it. Basically, yeah, we'll just go through things as we go. Here's a periodic table that I'm gonna fill up, probably, maybe. I'm not exactly sure, but I just put it in here in case we needed it. Basically, the main thing for chapter 8 is it's a lot of thinking about stuff, and so my goal today is to just sort of help you along in thinking about stuff and kind of show you like how to think about it. If that's helpful, hopefully it is. And either way, we're just going to practice some of the questions you're going to see on my fans on. Hopefully that's not really annoying. I'll turn it off in a second. But let's do this. So this is, I mean, we're doing an electron configuration, but this one's not too big. So first question is to just find the electron configuration for bromine, just a neutral atom of bromine. And then we're going to find what the effective nuclear charge is for one of bromine's valence electrons. So go ahead and give that a try and see how you go. And then just raise your hand once you finish the question. It's not a race, it's just for me to know when to start again. And I'm gonna go turn off my fan. Okay, fan is off. So yeah, give this a go. See where you get. Raise your hand when you're done. Okay. All right, let's go over it. I know I'm going a little fast. Oh. There we go, I put your hands down. I know we're going a little fast, but you know, I want to get some time in here. So first off, let's just find the electron configuration of bromine. If you want to stick yours in the chat right now, you want to type it out, and or you could thumbs up people who have the same question or same answer as you. See what you got, and then I will do it. We will go through it. Is that a really long one? Oh, never. Okay, maybe just do the. It might be really long. Oh, somebody got it. Okay, we got a thumbs up in there. So I didn't realize it's really long, and I just made you type it all out. But I was thinking boron, but no, this one's really long. Okay, let's do it. I can't actually tell if that's correct, but I imagine it is. Let's check though. So again, with all electron configurations, you start here at the 1s, and so we just write our line out as we go along the periodic table. So we start at 1s and fill up each. Hydrogen and helium represent the 1s. So we put 2 electrons in there, and now it's full. And so we move down to the next row, which is 2s. Fill that up, so lithium, beryllium, and then go all the way across the periodic table to 2p, and we fill that up as well. you get all the way to neon. So 2p6, so 1, 2, 3, 4, 5, 6 to neon. Okay, and then back down to this row. So that's the 3s2. Now we're at magnesium. I probably should have put like a square here. That's always a good thing to do, of like where you have to end up. So I know I have to end up here eventually. But we're at 3s2, and then we go 3p6, right? So now we're at argon, bound to the 4s. You can also fill the 3d first if you want to. That's more important for like the transition metals, but we'll fill 3d first because consistency. But it really doesn't matter a lot for the order. But it's nice to have all the 3s together and grouped together anyways. So yeah, let's go 3d10. So that fills up this whole row. And then let's fill up the 4s2. Okay, 4s2 right here, the potassium, the calcium. And now let's get to the 4p section. So 4p, and then we're going to go to boron. Oh no, bromine. 1, 2, 3, 4, 5. So that's 5 electrons in the 4p, and that gets us to bromine. Cool. So does anybody have any questions about that? We've got lots of, we seem to all have the same. Yep, cool. We got the noble gas configuration, which is good. Does anybody have any questions about that process that they would like to clear up? Or no, maybe? Cool. Okay. Just let me know. But we can do more of these if you want to. Okay, so now that we have that, I'll just write down the noble gas configuration here. What is it? 4s. Oop, no, that's fine. 3d10, 4s2, 4p5. And if you have these swapped, you just have to be careful as to what is actually the valence and what isn't. Right, because the 4 would be the furthest out energy level, where the furthest out the electrons would be. Right, if you're picturing sort of a bulb in your head of all these energy levels, it's N is 1, N is 2, N is 3, N is 4. 4 is the outer shell in this case. Right, so that's why, right, because we need to know that for effective nuclear charge. Right, so let's write down the equation for effective nuclear charge. Does anybody want to tell me the equation in the chat? And if you don't have to write like this sub, I mean, yeah. What equation do we use for effective nuclear charge? Z is equal to N minus S. Yes. So Z effective, is it N? I mean, I know that. Is the variable N? It must be. I'll just trust that it is N. But that is the, oh, I have it here, wait. Oh, no, it's Z. Z. There. Very close to N, just flipped.
Is that what our atomic number is going to be?
Yeah, exactly. So Z would be the atomic number, and then Z effective is what we're looking for. And then you subtract, what is the variable they use? S, which is the shielding constant, right? Right. No worries, Patty. I understood what you got. You got the equation right, so as long as you get it right, variables really don't matter as long as you put the right number where the variable is supposed to be. Okay, so there's the equation, and now we can do the calculation, right? Remember, there's these Slater rules. And Slater rules is basically just a way to describe the shielding of an electron, right? So this guy I think he's a statistician or a mathematician, I'm not sure. Or maybe he's a chemist, I don't know. But it's very statistical, maybe some physics in there. So what are the things we have to remember about Slater rules in order to do this calculation? Does someone want to give an explanation, a shot, or of how we actually go about to do this?
For Slater's rules, there's going to be 3 numbers. The first one is going to be for valence electrons, and you're going to multiply that by 0.35 because we will not be working with D or F. And then the next one will be the core electrons, if I remember right, which is 0.85. And then in the very, very end, the ones that are going to be left over will be multiplied by 1 because we will not be working with a number that is D or F, I believe.
But the
Yes.
core electrons, it's not all of them. It's just the ones that are on the n-1 shell.
Right. Cool. Exactly. Oh, no. Oh, that's fine. So I just closed my PowerPoint and I was like, oh God, I lost everything. But it's fine. Just give me a second. Yeah, so it's not all of the core electrons. It's every core electron that was good. I actually, okay. Let me not try to talk and do stuff. But yeah, so yeah, like President just said, it's not all the core electrons, it's all the core electrons at n-1, right? And then all the leftover ones, we just multiply it by 1, right? I'm just making sure, yes, okay. So that is sort of the numbers you have to remember for this stuff, right? This list right here is very important. I mean, it's how you're going to answer these types of questions, which you're definitely going to get one on a test. So let's actually write out what it looks like. So you can write it like this. So Z with like a little star, or just write effective. Really doesn't matter, of bromine. And remember this calculation is only for one valence electron. So we're looking at one guy out on the end, out at the edge of an atom, and we're saying how much pull, right? Because I didn't say this at the start, but effective nuclear charge is how much positive charge, how much an electron is affected by a positive charge, right? So we're looking at one little electron and how much of the positive charge is it actually affected by, right? So here is the calculation. So first up, we take the number of protons of bromine, which is 35, right? And that's just the atomic number. Okay, and then we subtract this S, and we can construct this S with these numbers. So what we do is we're going to put some numbers in here. Oh, no, it's subtract. Oh, it's fine. No, this is right. I'm writing it a little bit differently than what you might have seen, but just remember, yeah, I'll write it like this. So it's a little bit more descriptive. So there's a few parts. Okay, so we're gonna have valence electrons, core electrons, but only in the n-1 shell, and then the leftover ones, right? So what is the actual valence, like what is the n of the valence electrons? Let's first answer that. What was the simple way of doing Z effect? I keep forgetting. I'm not sure either. that doesn't recall anything in my brain. There's like a trend for ZFF. I don't remember a simpler way.
No, it's not a simpler way. It's just like you kind of ignore all the rules and you just minus the core electrons, I think, something like that.
Oh, yeah, I'm not sure. That doesn't ring a bell for me, but maybe it's something you've learned that I didn't. I don't know, but yeah, I don't remember. What did I even ask? I forget the question that I asked. Oh, what n value are the valence electrons at? 4, exactly. So it's all the ones here on the outer shell. We already kind of talked about that. So n is equal to 4. So that means that the core electrons are going to be in the n-1, which is 3. So we're going to look at all the electrons in the valence shell of 3. Okay. So
do you mind if I ask a quick question?
Sure.
How do you tell the valence shell when you get to ones that are much bigger than the second row?
How do you tell? Like the ones? Okay. Like, well, it's just the one that goes in order, right? So it's usually the largest. It's the one that's the n that has an orbital that isn't full, like completely full. So you see how like this 4p it only has 5 electrons. So we can say, okay, well, those ones, you ran out of electrons once you got to that spot. So that must mean it's at the very edge. It's at the end. It's the valence. And so that's how you can kind of think about it in a different way. Is like, okay, well, where did I run out of electrons? It was in the 4p. So that means n is equal to 4 is the valence electrons. Does that make sense, or do you want like another way to sort of do it? The other way to sort of do it is just to like say like, oh, it's the greatest n. I don't know if that would trip you up anywhere. I think it should always be the greatest n. But if you're in like the 3D, it can get mixy with the 3D orbital. So I think it's better to look at the n that isn't exactly full. Does that help?
Yeah, no, that helps a lot, actually. Thank you.
Cool. Awesome. I think the simple Z effective is just the atomic number minus the core electrons, but you don't multiply them. Okay. Cool. That's like a fast way to do it. Okay, so let us get back to this. So it's all the electrons in n. So we're going to multiply all the electrons in n is equal to 3 by 0.85. So let's put that as our first term. And I'm just going to leave the valence electrons till the end, just for now. So that's going to be everything in here. So 3s and 3p and 3d, so that's going to be 18 electrons. Makes sense? That's how you grab those. So everything with a 3 will be the one you multiply by 0.8. So let's multiply 18 by 0.85. Sorry, I say decimals out loud all the time and they're completely wrong. So if you ever hear me say a number that isn't what I'm writing, like I don't even know what I just said, but you multiply 18 by 0.85 for the n-1 shell. Okay, cool. And so the leftover ones are everything else. So that's here. So we have 2, 4, so 10 of them. So you do 10 times, I don't know why I put it here. Let's go in order. So 10 times 1. So that's everything else in here. And then the final trick that you have to be careful of is when you're looking at the valence. I guess I can look over here. Sorry for switching. I always have to be conscious about switching a bunch. But the trick for here is what? What sort of trick do we have to pull off before we can actually do this calculation?
Isn't it that we have to remember our valence is going to have to be 1 less than what we actually have because we're calculating for 1?
Exactly. That is the main thing people forget to do, so do not forget to do that. Remember, Z effective is for one little electron at the end. It's usually valence electrons. You can do it for core, but I think it's, yeah, but so it's for one electron, okay? So don't forget to you have to take that one electron out of the equation because it doesn't affect itself. Hopefully that makes sense. So you can't include itself in the calculation because it doesn't affect itself at all. It is itself. Hopefully that makes sense. So that's why you have to take away a valence electron. I know I'm being very detailed with this, and hopefully it's helpful. So instead of taking 7, because we have 2 in the S and 5 in the P, so instead of doing 7 times 0.35, we have to do 6 times 0.35 to isolate that one electron. Do not forget to do that. I'll make it very specific, so hopefully you don't forget to do it. And then you can do that calculation. That is perfect and set up. And just remember that I subtracted here, and everything else is added, but it'll all become a negative number. You have to be careful with your brackets. Okay. So hopefully maybe someone can put that number in the chat. That reasoning doesn't get the same answer. Yeah, so yeah, I don't think that's just like a shortcut. You shouldn't actually do that to like actually answer a question. I think it's just more of like a shortcut to get a general idea of the Z effective, but you can also just remember the periodic trend for the Z effective, which is, you guys should hopefully be memorizing those, all of the trends, because those are super, super important. Even moving on into second year, you're going to want to know those, so make sure you memorize those. I don't think the simplification is actually accurate. Yeah, I imagine it's not. I imagine it's not a very good way of doing it. Honestly, this isn't very accurate either, because again, it's a lot of statistical stuff. Answer 7.6. Okay, so somebody did it and they got 17, which is much different than 7.6. So yeah, I've never heard of that. I'm sure maybe you went over it. But yeah, it's definitely not something to like answer this type of question with. Maybe it works for like smaller molecules or smaller atoms. But yeah, so hopefully everybody got 7.6 and everything is good. Does anybody have any questions about finding am I talking too much? I always talk too much for like the first question. But yeah, let me know if you have any questions at all about this.
Are we going to be doing any more ZEF equations tonight?
I don't have any. We can. We're gonna look at the trends now, which might not take very long. If you want to do another one, we can.
Oh, it's whatever we have time for. If you got a schedule, I totally get it.
No, I mean, this is fine. This session's for you guys. So if you want to do something, I'm down to do it. You know, it doesn't, I just pick stuff to do, you know, that I think is important, but it's, you're the guys who are the ones taking the class. So like, yeah, I mean, we might go through this. I think we'll probably have time at the end. I can do another one really quickly, and then we can get another practice with electron configuration. So I can probably squeeze that in because I don't think these will take too long, the ones I have left. So I'll try to leave some, like, we'll do like 10 minutes at the end to do another one, because yeah, that one is definitely a really good question that you'll definitely see again on a test. But yeah, if anybody has any questions, just let me know and we'll move on, and just interrupt me or put it in the chat. So let's do this one. So this is just looking at periodic trends. Okay, so I've given a list of stuff, and I haven't checked this question, so it might If one is kind of hard to choose between, just go with your gut, and then we'll work with it and talk about it. But there's this list of equations of cesium, fluorine, phosphorus, silicone, and magnesium. And basically the first one, I want you to, this part isn't supposed to be here. I switched the order of this question. But first one, arrange from largest to smallest effective nuclear charge. And then for B, it's supposed to be B, arrange from biggest to smallest in terms of atomic radius. So that's just recognizing your periodic trend stuff. So go ahead and do that to the best of your ability right now at this moment. And then raise your hand once you've got a list for both of them, and then we will talk about it. Hopefully you guys aren't super busy. I know sometimes the week before reading week can be either real crazy or the week after is really crazy. It just depends on when people put all of their midterms. But yeah. Give it a try. My Monday and Tuesday are really crazy. Just hoping to get through Wednesday. Yes, me too. I had, just, I don't know why it works out like it works out, but professors always just put everything in one spot. I think they talk and like plan it out, I swear. But yeah, just got to get through this week and you have a nice break. Thought I was on top, but I forgot a lab due in 2 days. Oh no. Oh, that's me. I always forget about things and then end up doing them within like 3 hours. But yeah, especially if you have a lot of things, it's so easy to just forget something. Like, oh crap, I have a whole assignment to do in like 2 hours, I guess. Okay. And if you're having trouble with this stuff, again, like I said, I haven't checked this list, so if something's confusing, just try to organize the rest of them, and we'll talk about it, because I didn't get a chance to check this. Actually, I'm going to check it now. Okay. I think this list is okay. Nothing too indescript. Okay. Okay, hopefully. Okay, let's talk about it. Again, just to not sit here but yeah, let's talk about it. Okay. So the most important trend right now, that basically you can base everything off. Well, there's two ways you can think about the trends that in a way you won't have to memorize them if you just base kind of logic, or you can just memorize them if you don't want to think about the chemistry. But the most important one is effective nuclear charge, because a lot of things, effective nuclear charge is dependent on shielding, essentially, and shielding is how much an electron is blocked by the other electrons to the nucleus. So effective nuclear charge is really important because a lot of things are dependent on the shielding, and can be thought about in terms of like, oh, this is the shielding. Or another really great one that if you get down pat and sort of thinking about, it's not like it's less important for chemistry, but it's an easy way to sort of remember these things and think about it logically, is also atomic radius, because atomic radius, if you understand what a smaller versus a larger atomic radius actually means, it can help you think about things a lot easier. So that's sort of the goal here. But the trend for effective nuclear charge that you can memorize is increasing this way and increasing this way as well, but not as much. So it doesn't increase as much going from bottom to top, but going from left to right is a pretty good trend that you can base stuff off of. So if you just remember that, the effective, you can even write it on your periodic table so you can look at it all the time. So that's, if you know this, you can just base the list off of that, right? So the smallest effective nuclear charge would be around here, and then the largest would be around here. Okay, for effective nuclear charge. So let's write that list. So cesium, first up, is all the way down in the corner. So it would have a what? To have the largest. Well, I guess we can look at the comparing these two, because these are sort of on the opposite ends. Somebody.
Would it have the smallest because it's also kind of like really far from the protons?
Mm-hmm. Yes, exactly, because it's also, we'll talk about atomic radius in a second, but that was good good thinking as well. And so yes, cesium is at the bottom here, so it's the least in this case. And then fluorine would be the largest because it's all the way up here, which, you know, is both of the increase. You see how I'm sort of using this to analyze this stuff, hopefully.
Do you mind if I ask a quick question?
Sure.
So if I remember right, when ZEF controls the radius, I'm just trying to make sense of it all before the test.
Yeah.
The larger the ZEF, the smaller it's going to be because the more protons the electrons are feeling, right?
Exactly, yep. So, yeah, okay, we'll just talk about it now, I guess. So, yeah, if you think about it, like, we'll look at fluorine and cesium. Fluorine is, you can also think about electronegativity. We know fluorine is the most electronegative atom on the periodic table. It really likes electrons, so it's very tight knit, right? It's very, very compact, and that means its shielding is very, very high, right? Because yeah, there's a lot of electrons in there, and they're all being squished in, right? Where cesium is the largest one, or one of the largest ones, and its electrons are very far away from the proton, right? Or from the protons, yeah, because they would all be spread out. So, what am I trying to say here? So the pull that the electron in a cesium atom, because it's so large, the pull of an electron would be much less to the proton would be much less than in a fluorine because it's so compact and small. So that's sort of the connection between atomic radius and cesium. It's a great way to think about it, or atomic radius and effective nuclear charge. You know, the smaller the atom it is, the larger the effective nuclear charge is going to be, because the electrons are closer to the protons when they're really, really small. And if cesium is all spread out, then the electrons are super far away from the protons. Hopefully that makes sense. So that's a great way to think about it. So, and if remembering cesium and fluorine as a way to compare is also really great, because they're on the opposite ends of stuff. So if you just remember, you know, comparing cesium and fluorine, you can sort of put it all together, and maybe, I don't know. I'm just trying to give different ways to sort of think about this stuff. So yeah, hopefully that answers your question. I rambled, but hopefully it did. So let's fill in the rest of this real quick. So we also have phosphorus, which is right here, and then silicone is right behind it. So that can be kind of hard to distinguish because, but you know, generally, since they're so close together, but generally, you know, it increases going this way. Hopefully my camera isn't mirrored. I don't actually know. So we would say phosphorus is over here, and silicone is over here, and then where's magnesium? Magnesium is over here, which is further this way, meaning has a lesser effective nuclear charge than silicone. So we put magnesium over here. Okay. Somebody in the chat. No, that's just my notifications. So smaller radius means bigger is ZEF. Exactly, because if you just remember, it's because the electrons are so compact in there if the radius is smaller. Makes sense? And there's lots of reasons for that. And if you're interested in learning about like why all of that is, you know, that's really great. And it's an interesting thing to learn about. But you can also just remember stuff. That's totally cool too. So here's the final list. We have fluorine, phosphorus, silicone, magnesium, and cesium is the smallest effective nuclear charge. And so for the radius, what would it be? The same, the opposite, mixture of both?
Wouldn't it just be, you would just flip the list?
Exactly. It would be, yeah, the opposite.
Yeah.
Exactly, because they're an inverse relationship. So the largest radius is cesium, and then magnesium, silicone, phosphorus, fluorine. Yeah? Is everybody okay with sort of analyzing that stuff and the relationship between those two? I mean, there's a relationship between all of them. They're all really important, but there's ones that kind of make more sense than the others. Yes, hopefully. Cool. If not, ask questions. I love answering questions. It's fun. But if not, we'll move on from this. And, you know, always, if I'm moving too quickly, always just interrupt me or message me privately or what have you. I'm just trying to move a little bit quicker. So there's atomic radius of normal atoms, which is more just comparing how big it is and comparing to other atoms, right? So cesium's large, fluorine's small, and you can say a lot of things because of that. But there's also atomic radius. Another relationship you have to know how to analyze is the atomic radius of ions, right? Because the atomic radius will change depending on how many electrons are in it. Like if you just, it's really good to think about it physically. If you can picture in your head like an actual atom, putting more electrons in it will do something, taking more electrons out will do something. Right? So go ahead and try this out. Get a list. So the A is just any atom. It's just, I guess it should be I for ion, but I already exists, so just A, any atom, and any ion, I mean. So give it a go. And if this is confusing, just, I don't know. We will go through it. Okay. Okay. Let's talk about it. Just move in a bit faster so we can get to stuff. So a good way to think about this is like a group of people. Like let's say each electron is a person and all the people are connected with their arms straight out. And let's say there's one person in the middle and everybody wants to be around that one person in a circle and everybody's connected like this. If you add another person, add another electron, the circle becomes larger, right? So everyone, once you add someone, everyone would get farther away from the center, from the person in the center. If you take away people, the circle will constrict and get closer to the center, right? So for ions, to order them, something that has more electrons will be larger than something that has lost electrons, because effectively all the electrons, once there's electrons removed, the other electrons that are still in the ion can now have a larger pull towards the center because it's not distributed about, more electrons, right? So each one of them has a larger pull into the center because there's less of them in there. Does that sort of make sense? Hopefully. Maybe. So I don't know if your hand was still raised from, I just lowered so many hands, but if that was a question, you can just, but if it wasn't, I just lowered it. So let's look at these. So we have 3 plus, and 7 plus, and then 1 that's 4 negative. Right, and please stop me if I'm not doing this correctly. I'm pretty sure I am. But I can always mess up my explanation, so hopefully I'm doing okay. So the more negative one, the atomic radius would decrease, right? Because, wait. No, that's not correct. Sorry, I'm getting confused. The more negative one would have more electrons, so the atomic radius would increase. And also the electrons, when they get in there, they want to get away from the other electrons. So that would even further increase the radius, right? Because they don't like the other electrons. They would get as farther away as possible. So you're adding in more electrons, and they all don't like each other, so they're even farther apart as well. Right? So that's why we put the 4. Oh, no, I put it on the wrong side for the wording. Let's write this out again. Let's put the large to small. Okay. So the largest one would be the negative anion because you added in more electrons, has a larger negative charge. They all want to get away from each other, and there's less of a draw into the center as well because it's distributed among more electrons than normal. Hopefully I'm doing okay in explaining this, and please stop me if I'm not, or yell at me or something or correct me, but I should be okay. And then so for the A7 plus, it's lost 7 electrons, so the electrons that are actually left in there can now have a larger draw into the nucleus, and so it gets smaller. Oops, that looks like a 2. So the smallest one would be 7 plus. So we stick the A plus over here. Oh, this would be 3 plus, and then the A plus just in, so the more positive charge is the smaller, and the large is the negative. Did everybody else get that? I hope so. Right? Because sometimes I can think about things logically and then get it wrong. So yes, okay, cool. Cool. My worst nightmare is coming in here and explaining something that I think logically makes sense and then just not be understandable at all. But okay, cool. So everybody got that. And so just remember groups of people, whatever you want to remember from that spiel. If you're confused on that stuff, groups of people all in a circle. You add more, they're farther away. You take out more, they're closer to the center. Okay. So let's do this again quickly. Well, I'll just talk about it so we can do another effective nuclear charge, okay? So ionization energy, the energy that it takes to remove valence electrons. So it's the energy that you need to have to pluck an electron out from the valence shell, right? And the trend is increase this way and increase this way. Yes, that makes sense to me. Cool. So again, you can think about this in terms of atomic radius. If, let's take fluorine, for example, it's really, really small and compact, and the electrons like to be where they are. They're really small and in there, and they're happy because they're nice and close to the proton. Right? It's going to take a lot to get them to get out of there, right? Because they're happy, they're nice and compact, and as close as possible to the protons as they can get. It's going to take a lot of energy to try to get them out of there, right? So smaller, more compact atoms are harder to remove the electrons from than ones that are really far away. And like cesium is really far away. The electron at the edge of cesium doesn't feel a lot of pull from the proton. So it's a lot easier to take off than a fluorine, right? Makes sense? Hopefully. So if you ever forget ionization energy, think about small ones, harder to take the electron, large ones, easy to take the electron, right? Okay, so let's look at this quickly. Where's potassium? There it is. Okay, why did I pick? Why did I pick ones that were all the way over there? That was weird of me. I don't know why I did that, but anyways, we can order these. So if they increase up and increase over, the one that's furthest down and over is potassium. So this is the smallest. And remember, this is an energy value. It's not like a physical thing. Ionization is an energy value. It's just an amount of energy you need to take this electron off. Okay. Whereas atomic radius is something you can sort of picture. You can sort of picture stuff for the effective nuclear charge and stuff, but yeah. So the smallest would be potassium because it's the farthest down and over. The largest would be beryllium. So this gets kind of, I don't know why I made this question like this, but it gets kind of like hard because it's like, oh well. But this is just kind of applying this general. So beryllium is the farthest up and over. So that would be the largest energy value to take off the valence electron. And then if you go down, Mg, and then it'd be Na because Mg is below beryllium, so it'd be slightly less. That's greater than salt because salt's over more. And then calcium would be down here. And Na and calcium you can't really distinguish against. So, right, because Na, if you're comparing to Mg, Na is 1 over, so you'd say, okay, it's a little less than Mg, but Ca is in the same vertical, but 1 down. So Na and Ca would sort of be at the same energy. And I've actually been asked a question like this on a chemistry test where part of the list was 1 was equal and it's sort of confusing. Like you'll have a list like this where 1 is equal as one of the options, and you're like, wait, is it equal? And you just have to look at the trend and realize, oh, I can't really distinguish between NA and CA, with the information I have. So effectively comparing these to the rest of them they're equal. That is a valid thing, and you might see it. So if you see that, just don't be scared. Just try to think about the trend and where they're placed on the periodic table. Cool. And you can do lots of practice like this. It's like if you just pick random ones and then order them, and then look at real values. And so would H be about equal to BH in that case? Or BE? H is up really far. And BA, yeah, so essentially, yeah, you can't really distinguish between the diagonals here. Because it's kind of hard, right? Because they're almost equal. I mean, if you can look at a chart of all the energies and kind of see like, oh, okay, these are kind of really similar. Because there's a lot of cases with that as well. Hopefully that makes sense to everyone. If you just remember that atomic radius smaller, higher energy to take an electron off, larger, a lot easier to take an electron off because they aren't so compact.
So let me see if I got this right. For ionization, when you going up, it's increasing. Going to the right, it's also increasing?
Yep, going up and to the right, it's increasing. It's the opposite of atomic radius. Or is it? Yeah, yes.
Already got it. Thank you.
Cool.
Could you say when they're equal? You were saying that sometimes they would be like equal and you can't really say which one is more or less.
Yeah, so that's kind of like in the real world, like values that you'd get experimentally, they're not exactly equal. But just in terms of this like general trend that we apply to the periodic table, some of them you can't really distinguish against. Like I could have picked a totally different set of like if I picked this, and this, like those are really easy to distinguish because BA is all the way over here. So this would be the smallest because BA is all the way down here and down, right? So BA would be here, and then iodine is all the way over here. So we put iodine there, and silicon would be in the middle. But because these are so close together, sometimes the trend isn't applicable to like determine which one is actually, because like for NA and CA, there's no information I can use to say, okay, well, NA has to be larger or CA is larger because of this and this. There's no information that I can use to distinguish this besides just using like actual values and looking at the actual values. So this is only in the case of like applying the trend that you memorize and stuff. Did that answer your question, or did I just say nothing related to what you asked?
No, really good. Thank you.
Okay, cool. Cool. So we do have time to do one effective nuclear charge. And that was the last of my questions too. So let's do an effective nuclear charge question. And if you want to leave, you can. You don't have to stay if you don't want to do another one. But I'm going to do another one. If you leave, then thank you for coming. Let's just do another example. Can I not erase this? I guess I can't erase this. Here, let me get another periodic table. Down here. Yeah. And if you have any questions about anything we talked about today, put them in the chat and I will answer. So what do you guys, we could do like We'll do phosphorus. Let's do an ion. Let's do phosphorus -3. So if you're asked effective nuclear charge, you always need to look at the electron configuration, right? So even if you're not asked for the electron configuration, you have to find the electron configuration. So do that. And then, yeah, you do Z. Those are the steps to doing an effective nuclear charge. Okay. So I'm going to leave like 2 minutes to do that. And then I will talk about it, and then we shall be done. Ba-da-ba-da-ba. So yeah. Okay, that wasn't very long for you guys to try it, but hopefully you got some things set up. So let's do it. So first step, like I said, electron configuration. So we want to get it to here. And so let's just fill it out. So 1s2, starting here, going to helium, and then 2s2, 2p6, and now we're at neon. Okay, I'm just going through this a little quickly, but if you're confused, it should be okay. But if you're not, just let me know. So now we go down to 3s, so 3s2, and now we're in the row that we need to be. So we jump over to 3p, and it would be 3. But what do we have to do? Because it's an anion, what do we have to do? Because it's p3 negative. You guys still with me? Okay, we got some people typing. Add 3 electrons, exactly, right? So if you have an ion that you're doing an electron configuration for, remember, if it's a negative ion, you have to add those electrons, because if you have a negative charge, it means this atom has more electrons than it normally does. So you have to add the number of electrons of the negative charge that you have. If it's positive, you have to take away electrons, right? Because like we said, we've gone over this in the last few chapters. If it's a positive charge, you've lost electrons. If it's a negative charge, you've gained electrons, right? So in this case, we gained 3 electrons. So we have to add in 3 electrons to this. So that's just doing 3p6 rather than 3p3, which makes it isoelectronic with argon. Isoelectronic meaning same electrons, same number of electrons. It's a good word to know. Okay, so now we have our electron configuration. We can do the calculation. So let's set it up. So first we take the atomic number, which is 15, even though I covered it. So 15, that's the number of protons. Subtract with the square brackets. So remember the numbers. So for valence electrons, it's 0.35. For n-1 electrons, it's 0.85. And then for all else, it's 1. So remember those, have those memorized. So let's do the n-1. Well, first, what n are we in? What is the valence n? Okay, I'll just answer. Because, oh, somebody's going to answer.
Correct me if I'm wrong, because this is the thing I always script on. Is it 8? Correct me if I'm wrong, because I feel like it's 8.
Okay, so that's the number of electrons that are in it, but what n is that? So you got it right. That is the number of electrons that are the valence electrons, but like what n are we working it in for the valence? Right? So you know, because you did it. So it's 3. So n is equal to 3 for the valence. And we need to know that because we need to look at what n-1 is. So that's 2s, or for n is equal to 2. Okay, so those are the two things we need to figure out. You need to figure out what n your valence electrons are at, and then you find what n-1 is, and that will distinguish your numbers, and that's all you need, right? So for n-1, we have 8 electrons in it, right? So 2 here and 6 here. So 8 times 0.85 for your n-1. Let me write it here. Okay. Add, because I'm going to subtract it all here with this subtraction sign. So now I'm adding them. Be careful about that too. Just do it the way that you like to do it. And then for the all else is just the 1s2. So that's only 2 electrons times 1. Okay. Plus, now the valence. So the valence, again, remember we have to subtract 1. So right now we have 8. But remember we have to subtract 1, so we're actually going to multiply it by 7. And 0.35. Square bracket at the end, and then you can do that calculation, and that is it all set up. So that's all you have to do for those. You find what valence you're in, find the n-1, and then get the numbers right, and then do the calculation right, and then you're good. That is, so you do need to do your electron configuration correct as well. Okay, does anybody have any questions about that? It's good to look at that too, because it gave you an example of how to do it with. Okay, Maddie got 3.75. Should be good. Let me know if anybody else got that. So yeah, is anybody, other than that, that's all I have to do today. If you have any questions, let me know. And then you can always message me if you have any questions, and we can go over it in PAL. But yeah.
Would you have any tips for helping with this type of calculation?
Yeah, thank you guys if you're leaving. Thank you for coming. I appreciate it. Yes, so just decide how to work through it, like through calculating it.
Yeah, through calculating it, because what I seem to be doing is where the valence electrons are,